In this video, we're working on being able to explain the relationship that occurs in right triangles. Once we find that relationship, we're going to use it to prove if a triangle is right or not. And then we're also going to use it to find the missing side length of a known right triangle. So right triangles are defined as triangles that have a right angle. It doesn't matter where the right angle is situated as long as it is exactly 90 degrees. Okay, so this would be a right triangle. This side length right here is called a leg. And this side length right here is also called a leg. It doesn't matter which one is which. We usually like to call this one A and this one B, but this one could be A and that one could be B. It really doesn't matter. However, the side length that is across from the 90-degree angle is always, no matter what, the hypotenuse. Every single time. So just getting us some vocabulary out there about right triangles. So right triangles are pretty special to us. Not only because they have a right angle, but because they have this very interesting relationship about them. So I'm going to go ahead and draw a right triangle. Okay. And if I wanted to use this side length right here and create a square out of it, what would its dimensions be if I called this side A? Hopefully you said that they would all be A's, because a square is one of those really cool things that has a neat relationship where every single side length is the same. So what would be the area of that square? I think we find the area by taking length times width, but in this case the length and the width are the same thing, so we could do A times A, also known as A squared. So the area of that square is A squared. Okay. Now on this side length right here, let's call it B. If I made a square with it as a side length, what would each of its side lengths be? Hopefully you said that they would all be B's, and so the area would be B times B, or B squared. Okay. If I then created a square off of the hypotenuse, oops, that's a pretty ugly square, but you get the point. Okay, we would call that C, and so all of its side lengths would be C, and so the area would be C times C, or C squared. Okay, so there's a very interesting relationship that happens only in right triangles. The A squared plus the B squared happens to be equal to the C squared. Let me give us an example of this. I'm going to go ahead and switch over to a picture. Okay, here we go. Right triangle. We know it's a right triangle because it happens to have a right angle in the corner indicated with that little box. So if I was to count, what is the area of the square created off of leg A? What is the area of the square created off the leg A? It should be 9. Okay. What is the area of the square that's created with side lengths of B? Well, B is 1, 2, 3, 4, so 4 squared is 16. Okay, so that means C, the square created off of the hypotenuse with the side lengths of C, must be 9 plus 16. 9 plus 16 is 25. So the area, if I counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on, there's another group of 5, so that's 15. Here's another group of 5, so that's 20. Here's another group of 5, so that's 25. So I can count each of the little squares and I get 9 plus 16 is 25. So my question is, what would be the side length of C? It turns out that the square root of 25 is 5. So that means I must have taken 5 and squared it to get to the area of 25. So C is actually equal to 5 units. and we can count it. 1, 2, 3, 4, 5. Okay, same thing with this b squared. Okay, I got 16. The square root of 16 is 4, so that must mean to find that area, I must have done 4 squared and gotten 16. So if we look at b, it is 4. 1, 2, 3, 4. Why don't you prove that the why don't you prove that the square root of 9 is 3 and then confirm that a is a distance of 3? Okay, let's go ahead and look. I'll go ahead and clear all that ink, and I'd like to look at this one. So this one right here is our original triangle, our original right triangle. Okay, so we created a square with side lengths of a, which is the leg, and we got a squared. Then when we created a square off of b with a side lengths of b, and we got b squared. And then once again here, we created a square with side length of c, and its area would be c squared. Okay? If you look at this, this triangle is repeated 1, 2, 3, 4 times around that c squared, that hypotenuse square. Okay? It turns out that if you placed 1 and 2 in part of 3, triangle 3, you would take up all of b. And if you cut up 4, you could get a squared. All right, so just another visual. We'll be cutting that out in class in a little while. So let's go ahead and go back to some more work, and I'm going to work some examples. So this would be important for you to write into your notes so that you can use them for future reference. Now, when we start out, the Pythagorean theorem seems really, really easy. Okay, the Pythagorean theorem is not hard. If I give you a right triangle and I say, what's its missing side length? Or if I give you a triangle and ask if it is a right triangle. But this isn't where we need the Pythagorean theorem. We need Pythagorean theorem in construction, when we're finding the pitches of roofs. We actually use the Pythagorean theorem to estimate the heights of trees that we can't measure, the heights of mountains that we can't measure. Okay, your little range finder that you use when you're hunting actually calculates the Pythagorean theorem inside of it in order to find the range of things that aren't perfectly level with you. So let's do just a couple of examples. So what if I have a triangle and I don't know it's right? Okay, I am questioning whether or not it is a right triangle. But I do know all 3 of the side lengths. If I happen to know all 3 of the side lengths, I can actually prove or disprove if it is a right triangle. So let's say that this leg is 5 centimeters long and that this leg is 12 centimeters long. Then this one is 13 centimeters. And my question is this a right triangle? So the Pythagorean theorem says that if I take side length a and I find its area, that's a squared, and I add it to side length b and I find its area, so I'm creating squares, then I should get the hypotenuse square area. Okay? So I'm going to make a be 5 and b be 12, but it does not matter which one is a and b as long as the side length that we are thinking is across from the 90-degree angle is C. Okay. Turns out the hypotenuse is always the longest side length as well. So if ever you don't know which one's it, that one is always the longest. So I'm going to go ahead and just plug them in. So 5 is the length of A. I'm going to find the area of it. It's 25. I'm going to add that to B is 12. So I'm going to find the, 12, not be 12 squared, which turns out is the area of the square created with side lengths of 12, so I get 144, and that's equal to, well, it should be 13 squared, and 13 squared is 169. Okay, so the question is, does 25 plus 144 equal 169? So if I go over here, 144 plus 25, I get 9, 6, bring down my 169. So it is true. 169 is equal to 169. Is this triangle a right triangle? Yes. Why? Because the side lengths actually fit the Pythagorean theorem, which is a squared plus b squared equals c squared. So the area of the square created on leg A, the area of the square created on leg B is equal to the area of the square created by C. So I've just proven that that triangle is a right triangle. All right, let me give you another example. Okay, what if I know it's a right triangle? Okay, I'm 100% positive of it. And I don't know I don't know the hypotenuse. So let's make this be 8 feet and this be 15 feet. Okay, quick check. My hypotenuse across from my 90-degree angle is always C, and it's going to have to be larger than 15 because the hypotenuse is always the longest side length. So now I just substitute it in. I'm going to make the 8 be A, and I'm going to make the 15 be B. So I simply do 8 squared plus 15 squared equals C squared. Now I simplify. Do my exponents first before I do my addition. So 8 squared is 64 plus 15 squared. Ooh, what is 15 squared? I think it's 225 is equal to C squared. Simplify one more time by doing my addition. I'm going to combine my like terms. It's very nice. Both of my terms are constants. I don't have any variables in there. So I'm going to go off to the side here. 225 plus 64. 8 is 289. 289 equals C squared. Okay, my question though is, what is C? I don't want to know the area of the square. I want to know what the length of the hypotenuse is. So I can cancel out this squared by taking the square root. That will just leave me with a C. But if I took the square root of that side, then I have to take the square root of this side. So I can leave it as the square root of 289 equals C. That doesn't tell me what the side length of C, though, is. If I said, what is C, you could tell me it's the square root of 89. But if I said, what is the missing side length, I want you to tell me how many feet it is. So I might need to do a prime factorization to figure out the square root of 289. But it turns out I also know that the square root of 289 is 17, because 17 times 17 is C. So the actual answer to my question is that the hypotenuse is 17 feet long. And that's reasonable because 17 is larger than both 8 and 15. Okay, so if I'm missing a side length, I can simply substitute it in. If I'm missing the hypotenuse, I get a squared plus b squared equals c squared. If I'm missing the leg, I need to make sure to put it in appropriately. All right, so we just used the Pythagorean theorem to find a missing side length. Before that, we used the Pythagorean theorem to prove if a triangle was right. So I think that gets us to everywhere we needed to be. Have a great day.